Okay. Oh. All right, if you're tuning in on the live stream, we're just waiting for the class to log back in.
All right, Professor, you're back.
Are we good to go now, Ivan?
Yeah, it just disconnected and then reconnected. I don't know why it does that every time at the beginning.
Okay, well, we're here now, and that's what matters. All right, let's get rolling. So good morning, everybody. It's nice to see you. Just a reminder that the Chapter 2 quiz is today. So at some point today, you'll have to find an hour to take that quiz. Again, similar to the mini quizzes, all multiple choice, except you only get one attempt at doing it, and you have to have that submitted by midnight tonight. So make sure that you get that in. We are transitioning into Chapter 3, and I just want to give you sort of a 1-minute overview of what that's going to mean. Okay, so Chapter 2, we really built up the idea of what is the derivative, right? We were interested in how quickly a function was changing at a point, and then we were able to generalize that to how do we find the derivative function. We looked at that graphically, we looked at that with tables, we did a couple of applications like in economics. And so in math, when we do this kind of work, we look for patterns. So once we have patterns of things like the type of rate of change, what does it look like, we are able to get formulas, right? That's where formulas come from. So what we're going to do is we're going to take our work with derivatives and think about what kind of formulas that we can come up with to then use in Chapter 3. So I'm going to go ahead and switch over to the doc cam. All right, so where do these formulas come from? Well, a lot of them come from the definition of derivative. And for the definition of derivative, it is a limit. That's why we looked at limits for a while as we went. But the reality is most of the time we're not going to be using this particular limit to find derivatives. So this is the definition of derivative. And so what you see is when you apply it to certain functions, we are able to come up with formulas that we can always use. So for example, if we have a function that is a constant, so C is some number, right? So C is 5 or C is 10, something like that. If we were to apply this definition, right, f of x plus h, think back to our composite functions. If you try to plug in an x plus h here, you still just get that number, right? So nothing changes. It's always equals to 5. So really, this is the limit as h goes to 0 of the constant minus the constant, which is 0. We know 0 divided by anything is just 0. So what we find is this formula that if you have a function that is any constant, then the derivative is always 0. Okay? So if you have a number that's all by itself, the derivative of that number is always going to be 0. Okay? Similarly, if you were to apply this to a linear term, so mx, right, and you were to apply f of x plus h minus f of x, that means you'd be plugging in an x plus h, wherever you see the x, minus mx. If you do some algebra here, okay, the mx's are going to cancel, and you're going to be left with mh over h. The h's will cancel, and you will always get m, which we know to be the slope of the line. So what does that tell us? If you have a function that is a number times x, the derivative is just the slope of the line, okay? Now, this isn't meant to give you a whole big map of how to use this limit. This is supposed to sort of show you that we can come up with generalized functions to get derivatives. If you start doing this with other types of functions, you start to get patterns. So if we were to use the definition of the derivative on x squared, we would find that the derivative is 2x, right? Once we did some simplification here. If we were to do it on x cubed, we would find that the derivative is 3x squared. So all of this to say is that if we do this on enough types of functions, we start to get formulas. And so the first formula that we're going to look at today is called the power formula. And so we use this for polynomials and power functions. So a polynomial, that's your x squared, your x cubed, your x to the fourth. Your power function is your x to the 1/4 or x to the 1/2. So x is still in the base, but now we're just sort of including any type of power here. And the generalized formula for this is if you have x raised to some power and you want to take the derivative to get the general derivative function, the formula says that the power will come down in front and then we subtract 1 from the power. So let's quickly look at an example of this. So let's say we have x to the, 32nd power. Okay, what this rule says is that the power will come down to the front. So we have 32x, and then we have to subtract 1 from the power to the 31. Okay, so again, one of the key sort of elements of this is recognizing that we can use this formula. And we do that because we notice that x is in the base and it's raised to some number. Okay, so let's start practicing with some of this. So here are the 3 rules that we know right now. Okay, so we know that if you have a constant, so a number that's all by itself, then the derivative is 0. We know that if you have a number times x, where x is not raised to a power, right, just x to the 1, then the derivative is just that constant, the slope of the linear term. And then we know if you have x raised to a power, then the derivative is going to be px to the p minus 1. So the power will come down in front, and then we subtract 1 from the power. Okay, so what I'm going to have you do is I'm going to have you try a through g. Okay, so here's a bunch of terms where we can practice these 3 rules and see how we might apply them. I want to caution you for E, F, and G to be extra careful when you are subtracting 1 from the power. Because if you have a negative power or a fraction or a negative fraction, you just have to be extra careful and remember that when you subtract 1, what happens to that number? Okay, so I'm going to give you about 2 minutes, and I want you to try to sketch the derivative for each of these functions. So remember, you're going to get the derivative function just like we were doing when we were working with graphs. Okay, so take 2 minutes, check in with someone next to you if there's someone there, and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's go through these as we start learning how to apply our derivative rules. We want to get really comfortable with recognizing when we use which rules, because what we're going to be doing over the next several classes is adding on other types of functions. So the first thing is really to recognize what type of function we're working with. So notice here for the first one, we just have the number 7. There's no x there. And so 7 is just a constant. And according to our rules, if your function is a constant, then the derivative is just 0. And again, this is only if the constant is by itself, okay? Because we'll see in the next example, we have 10x. We said, okay, if you have a constant times x, then the derivative is just that constant. So here for the second one, the derivative is 10. So this is really important to understand the distinction between A and B, that A will go to 0 because the constant's by itself, whereas B will go to 10 because our constant is paired with the x, okay? Now for the next one, we have x squared, so we're going to use our power rule. So the 2 will come down in front, and then we subtract 1 from the power. So we get 2x to the 1. We don't typically write the 1 when we have powers, so we could also write this as just 2x, okay? Let's keep practicing our power rule here. So the next one, we have x to the 5th. So for the derivative, the 5 comes down, and then we subtract 1 from the power. So we get 5x to the 4th. For part E, we have x to the negative 4. So now we have our first encounter with a negative power. When we use this rule, the entire power comes in front, including the negative. So this is going to give us negative 4x. Now, if you have negative 4 and you subtract 1, you get negative 5. So that's the first sort of key time that we notice that we have to bring the entire power. So if there's a negative, that also comes in front, okay? And if you subtract 1 from a negative number, it becomes more negative. So just be a little careful with those. Let's see, we have x to the 2/3. So again, the entire power comes in front, so the whole 2/3. And then when we subtract 1 from the power, 2/3 minus 1 is negative 1/3, okay? So if you have a fraction that's less than 1, when you subtract 1, you're going to have a negative power. So be really careful with those. And then for the last one, we have negative 4/5. So that comes down in front. And now negative 4/5 minus 1 is going to give me negative 9/5. Okay, so negative 4/5 x to the negative 9/5. So one of the key things I want you to recognize here is that we are getting the entire derivative function. And as a reminder, the derivative gives us the rate of change of the original function. And so if we want to know how quickly the function x squared was changing at 1, we could plug a 1 into this function, or at 2, or at 3, or at 4. This gives us a mechanism to find the exact rate of change at any point in time by finding the entire derivative function, okay? Now there's a couple more things we can add on to our rules here. So the first is called the constant multiple. So what does that mean? Let's say you have a constant times your function. So we have one example of that in mx, right? That's already a rule. But what if you have a constant times x squared or x cubed? What happens when you try to take the derivative and there's a constant there? How does that work? Does the constant go away? Sort of what happens? So it turns out that we can actually pull the constant out front, which means that when we take the derivative and there's a constant, the constant is going to multiply the derivative of the function. Okay, so what does that mean? Let's look at a quick example here. So let's say we have f of x equals, I don't know, 3x to the 5th. What this rule is saying is that when you take the derivative, you're going to take that 3 and multiply it by the derivative of x to the 5th, right? So the derivative of x to the 5th, the 5 comes down, x, and we subtract 1 from the power. So 5x to the 4th. So because we had that constant multiplied here, it also multiplies the derivative. So we can simplify this, and 3 times 5 is 15, and we get 15x to the 4th. So that constant that multiplies in front of your term, okay, is part of the derivative. So again, that's different than if you have a constant that's all by itself, right? If it's all alone, it goes to 0. If it's part of the function, it becomes part of the derivative. And so what a lot of people do, and what we'll start practicing doing, is we'll say, okay, when the 5 comes down in front, it multiplies the 3 to give me 15, and then we subtract 1 from the power. So 15x to the 4th. So what's happening in the background is this constant multiple rule. Okay, so now we're going to practice that rule here. So we have a through g, so we have another set of functions that mostly now have a constant in front. So thinking about these rules that we know so far, I want you to try to find the first derivative for each of these functions. Okay, so I'll give you about 2.5 minutes. Try to sketch out the derivative, and again, be really careful when you subtract 1 when you have negative powers or fractional powers. Okay, so try it out, and then we'll go through it together in about 2 minutes. Okay, take about 30 more seconds. All right, so let's go through these. The first one is a little bit tricky. So I just want to remind you that pi is a number, right? It's approximately 3.14. So that means that this is a constant. There's no x here, which is the variable of this function, which means that when I take the derivative, it's just going to be 0 because it's a constant that's by itself. Okay, so be careful with things like pi's or e's. Again, if there's no x there, it's just a constant. For the next one, I have 4x cubed. So again, the 3 is going to come down in front and multiply with the 4. That's going to give me 12x. Now I have to subtract 1 from the power. And so I get 12x squared. Okay, again, the power multiplies into the constant that's in front. For our next one here, we have 9x to the 20th. The 20, the entire 20, will come down and multiply the 9. And I'm going to get 180x. And now again, I have to subtract 1 from the power. So here that'll be to the 19th. For the next one, we have a negative in front, so we have to be careful to make sure we don't lose that. So we have negative 3x to the 5th. When the 5 comes down, it's going to multiply negative 3, right? So we get negative 15x, and then we subtract 1 from the power here, and we get 4. So again, if there's a negative in front, when the power comes down, it multiplies just like you normally would. Don't get rid of that negative just for no good reason. It's still part of our solution here. And we have 6x to the negative 6. So similar idea as the last one, but now the negative is in the power. As I mentioned before, if there's a negative in the power, the whole entire power comes down in front. So negative 6 multiplies 6 to give me negative 36x. And again, be careful with negative powers. Negative 6 minus 1 is negative 7. For our next one here, we're going to be a little bit careful with our fractions. So the 1/3 will come down to multiply the 6. So 1/3 times 6 is just going to be 2x. And now we have to subtract 1 from the power. So 1/3 minus 1 is negative 2/3. For part G, we have 7x to the negative 2/5. So again, the negative 2/5 will come down in front, and I'll get negative 14/5 x. And now I have to subtract 1 from the power, giving me negative 7/5. Okay, so we have to be extra careful with fractions. It's really easy to lose sort of negatives or fractions or things like that as we go along. So we're just going to make sure that we pause and we double check any of our fractions or negative powers. So that's how our constant multiple rule works. So again, if there's a constant out front, it just multiplies the derivative. So the next sort of thing we need to be concerned about goes back to our original sort of rule, right? We said if you have x raised to the p, then the derivative is px to the p minus 1, right? So the power comes down. However, sometimes a function is not quite in this form yet for us to be able to use the rule. And so in order for us to be able to use this rule, it has to be written in this form x raised to some power, which means that if it's not written this way, sometimes we have to use algebra rules to rewrite it first into this form. So what the next exercise is going to do is it's going to give you 3 examples of where you need to rewrite this function first into this form. So you have x raised to the p so that you can then apply the power rule. So we're going to try this out. Hopefully you remember some of these from algebra, but the reason that we're doing these together is because if you don't, we want to make sure to sort of brush up on that. So again, if you're not sure what to do or how to rewrite it, that's okay. We'll go through it together. But if you don't know how to rewrite it, make sure you like put a box around it or something so that later on you can reference it if you don't remember. Okay, so here are the 3 problems we're going to look at. So A is the square root of x, B is 4 divided by x cubed, and C is the 5th root of x squared. So for all of these, the first step is going to be to rewrite these into a form that is x raised to some number. And I will say for the second one, you cannot take the derivative in the denominator. So that's why we have to rewrite this. We have to figure out how to get that x cubed term up and out of the denominator. So I'm going to give you about 2 minutes to try this out. If you are able to successfully rewrite these using algebra, then you can go ahead and take the derivative. If you don't remember, I want you to just give it a try anyway, right? It might have been a long time since you've done that. And again, that's the reason why we're doing it, because these are the ones that people often forget because it's been a while. So try it out. I'll give you 2 minutes and then we'll go through it together. All right, take about 30 more seconds. All right, so let's go over these. Again, I really want to make sure we understand how to rewrite these. This is sort of things that come up somewhat commonly, but a lot of people forget because it's been a while since they've been in an algebra class. So here we start with the square root of x. So again, if there's no number with the root, that means it's the square root. And the way that we rewrite that is x to the 1/2 power. Okay, so that's the rewrite. We haven't taken the derivative yet. All we did is we wrote this in an equivalent way. And so we can't do anything when we have the symbol. So we have to turn the symbol back into a power. Once we have it as x to the 1/2, then we can go ahead and take the derivative. So again, the power comes down in front. We subtract 1 from the power. And we get 1/2 x to the negative 1/2. I do want to take a minute to talk about how else we could write our answer so that if you see it written a different way, you remember how this works. But we'll come back and talk about how to rewrite all our answers after we do all three. Okay. So for the second one, we have 4 over x cubed. If you want to bring a term up from the denominator, you need to change the sign of the power. Okay, so the power here was 3. So in order to bring this up from the denominator, I need to write this as x to the negative 3. So I have 4x to the negative 3. So now I still have to take the derivative. Again, that was just a rewrite. I haven't done any other work on this yet. So when I take the derivative, the -3 comes down and multiplies the 4, giving me -12x, and I subtract 1 from the power to give me -4. The third one, I have the 5th root of x squared. Whenever you have another root, whether it's a square root, a 5th root, a 3rd root, you can write it as 1 over whatever that number is. So I can rewrite this as x squared to the 1/5, because the 1/5 is how I rewrite the root. Now, if you have a power raised to another power, you can multiply those two numbers together. So I can simplify this even further by multiplying 2 times 1/5 and write this as x to the 2/5. Now again, that step was all just rewriting the function. I haven't done the derivative yet. So now when I take the derivative, the 2/5 comes down, x, and I subtract 1 from the power. So I get 2/5 x to the -3/5. Now, this is totally fine to leave as an answer. So if you are entering something, say on Wiley Plus, and it asks you for the derivative, you can do a text entry like this. But there are ways that we can rewrite these that I want to make sure that you understand in case you see it written a different way. So we'll start with this first one. Again, notice the negative power. So what I can do, and I can do this in 2 steps, is I can take that x to the -1/2 and put it back in the denominator by changing the sign back to positive. So these are the same thing right now, okay? And then the 1/2 power is the same thing as the square root. So this is 1 over 2 square roots of x. So this derivative can be written like this, but it can also be simplified to be written like this. And those are the in-between steps. For this derivative, I have x to the -4. So again, I have this negative power. So I can put this in the denominator. Notice here that I don't have a fraction already set up like I did here, 1 over 2. So that means that the 12 stays in the numerator and that x to the 4th can go into the denominator. So only the x term is going into the denominator, right? Not the 12. The 12 stays right where it is. And so I have to change the sign of the 4. Similarly here, if I wanted to rewrite this, right, I have my 2/5 already, right, from up here. But now I have this x to the -3/5. I can bring this down and make the power positive. And then if I wanted to go one step further to have it closer to the original sort of setup here, if I wanted to bring the 5th power back in, I'd have the 5th power, and then notice the top is 3. So that would be an x cubed. So these are the same, right? So this is just one way you can rewrite it. So if it's been a while since you've worked with fractions and algebra and stuff, you may want to practice this on the homework before you take the mini quiz to make sure you're comfortable with sort of moving things around if you need to, okay? So again, if you start with a function in this form, sometimes the first step needs to be to rewrite it before you can take the derivative, okay? So we're gonna keep building on to our rules here. The next one is sums and differences. So what does that mean? That means when you add and subtract terms, how does that impact the derivative? So let's say we have one function plus another function, and we want to take the derivative, right? And this is also true for subtraction. Then what we can do is we can take the derivative of the first function plus the derivative of the second function. And if it's minus, then there's just a minus there. So what does that mean? As long as your terms are separated by addition or subtraction, you can just take the derivative of each piece. This is not true for multiplication and division of more complicated functions. We're going to have special rules for those next week. So That just means we're going to take the derivative of each piece as we go. So I'm going to have you try some of these, which are separated by addition and subtraction. But again, the idea is that you'll take the derivative of x to the fifth minus the derivative of 2x squared plus the derivative of 6x plus the derivative of 1. So you just take the derivative of each piece to get the derivative of the entire function. You'll notice that in B, C, and D, you're going to practice rewriting some of those terms first. So again, a good first step is just to rewrite the entire function, doing whatever algebra you need to do, and then finding the derivative. Okay, so take 2-3 minutes and see if you can sketch out the derivatives for A, B, C, and D here. Okay, take about 30 more seconds. All right. So for part A, we don't need to do any rewriting. There's no terms that are not already in the correct form. So we can go ahead and just do the derivative term by term. So we start with x to the fifth. The 5 comes down and we subtract 1 from the power. So we get 5x to the fourth. The second term has this constant multiple here. So when the 2 comes down, it multiplies the 2 in front. And I get 4x to the 1 power. Again, you can write the 1 power. You don't have to. It's up to you. The next term, so this is a linear term. So remember, if you have 6x, the derivative is just going to be 6. So when you have a number times the variable, the derivative is just that number. And then finally, the derivative of 1 is a 0 because 1 is all by itself. It's a constant and it's not attached to any variable. So that's just going to be plus 0. Again, we don't typically write the plus 0, so you don't need to write that. But since this is our first sort of day of doing these formulas, I'm writing it so we remember that the derivative of a constant is 0. For the next one, we do need to rewrite that last term. So I took an extra step here and I just rewrote the original function, but I turned the square root of x into x to the 1/2. So again, I took that extra step to rewrite it, but that's not the same thing as taking the derivative. So I still need to take the derivative of the function. So here I go term by term. The 3 comes down to multiply the 3, giving me 9x squared, because I subtract 1 from the power, minus, now here the 1/3 comes down, and I subtract 1 from the power. I'm going to be extra careful because it's a fraction. And I get negative 2/3 plus, from my last term, x to the 1/2, I get 1/2 x to the negative 1/2. Okay, so again, I just go term by term, carefully taking the derivative of each piece. For part C, I notice that I need to rewrite the second and third term. So I take a step to do the rewrite. So I have 10x to the 4th minus, now this was the 4th root of x. So I write this as x to the 1/4. And then here I had 2 over x cubed. So I bring that x cubed term up by making the power negative. So again, I haven't done the derivative yet. I've just rewritten it. So now when I do the derivative, the 4 comes down to multiply the 10, giving me 40x cubed, because I subtracted 1 from the power, minus, now I have x to the 1/4, so the 1/4 comes down, subtract 1 from the power. 1/4 minus 1 gives me negative 3/4. And then finally, the last term, the negative 3 comes down to multiply the positive 2, giving me minus 6x to the negative 4. So again, these can be a little tricky algebraically, so be careful that you're just really taking each one step by step and making sure that you're not losing any negatives or anything like that along the way. The last one, again, I need to rewrite because of this square root. So I take that step and I write the square root as the 1/2 power, and now I'm ready to take my derivative. Again, I'm going to be really careful. I see a lot of negatives here. So the negative 3/4 comes down to multiply negative 3. That negatives are going to cancel, and I'm going to have 9/4 x, and now I'm going to subtract 1 from the power. Negative 3/4 minus 1 is negative 7/4. Plus, now here, when the half comes down to multiply the 2, that's going to give me 1x. Now I'm going to subtract 1 from the power to the negative 1/2. Now I don't need to write the 1, right? I can if I want to, or I can leave it off. So that's going to be the derivative of this last term. Okay, so when you have terms that are separated by addition and subtraction, that's when we can do it term by term. I mentioned before that we cannot do that with multiplication and division, and that's when you're multiplying 2 functions together. So an example of when you cannot go term by term, right? If you had something like e to the x times x to the 4th, right? We don't know how to solve that yet. That's 2 functions multiplied together. We can't go term by term, only if it's separated by addition and subtraction. Okay, so moving right on, we're going to add a little more information here. So the next thing we'll talk about is the second derivative. We know from our prior work in chapter 2 that the second derivative is the derivative of the first derivative. So if we have a function that is a power function, x to the p, we know from all our work in the last half hour that the derivative is px to the p minus 1. Okay, if we want to find the second derivative of a function, we would take the first derivative and use the same rule. So we would take the power, it would come down in front, and then we would subtract another one from the power, right? It looks really goofy when you write the formula like this, but it just means we're applying the derivative rule twice. So for example, right, if you have 3x to the 5th, the first derivative, which is what we've been practicing, the 5 comes down, we get 15x to the 4th, right? That's what we've been doing. The second derivative means we just do that process again on the first derivative. So the 4 comes down to multiply the 15, giving me 60x, and we subtract 1 from the power, 60x cubed. So you just do the same process again on the first derivative to get the second derivative. So the power rule carries through to help us get to the second derivative. You just have to use it twice, okay? So let's practice some second derivatives. Okay, so here, parts A, B, and C. Notice that for part A and part C, you're going to have to do a rewrite. So you can do the first derivative, and you're going to want to do the first derivative first, and then you're going to try to find the second derivative. Part B is supposed to be a little tricky. Try it out. Try to remember what E means and how we would do it in this context with the power rule. Okay, but for all three of these, try to find the first derivative and the second derivative. All right, so take 2 minutes, try them out, see what you can figure out, and then we'll go through them together. Okay, take about 30 more seconds. All right. So for part A, we do need to do some rewriting before we can find the first derivative. So my first step is just to rewrite. So the 3 over x term, that one's a little tricky because we don't see the power as clearly as we do in other circumstances. So I just want to remind you, this is 3 over x to the 1 power. So we do have to rewrite that by bringing the x up and making this minus 3x to the negative 1. So that one's a little tricky. And then plus 3x to the negative 2. Again, I got to bring that up from the denominator, plus x to the 1/3. So now that I've rewritten this, I can go ahead and find my first derivative. So the derivative of 6 is a constant, right? And so the derivative of a constant is just 0. So that term's going to go away. The next term, the -1 is going to come down and it's going to multiply the -3. So that's going to make that positive, right? So we're going to have 3x to the -2 because we subtract 1 from the power. And again, it's positive because the negative from the -1 cancels with the negative or the minus in front of the 3. Next, the -2 is going to come down to multiply this 3, giving me -6x to the -3 because I subtract 1 from the power. Plus, now I have my 1/3 x to the -2/3. So 1/3 minus 1 is -2/3. So that's my first derivative. There's a lot of bringing in all the other things we've been talking about, but now I want to take that and I want to use it to find the second derivative. Okay, I'm a little worried about space, so I'm going to do my second derivative up here. Just because I have to write big enough so you can see. Okay, so my second derivative, I'm going to go to my first derivative and go term by term. So the -2 comes down to multiply the 3, giving me -6x, and then I subtract 1 from the power to the -3. For the second term, the -3 is going to come down and multiply the -6. The negatives are going to cancel. So I get plus 18x to the -4, because again, I'm subtracting 1 from the power. And then here, my -2/3 is going to come down to multiply the positive 1/3. So that's going to give me -2/9 x to the -5/3. Okay. If it's been a while since you've done a lot of fractions and the fractions are kind of like boggling you a little bit right now, definitely feel free to stop and to drop in help and to do some more practice on fractions because you want to make sure you're really comfortable with simplifying fractions as we go. So my second derivative looks like that based on my first derivative. For part B, I have x to the e. So remember, e, okay, is just a number. It's like 2.71 something. So we can still use the power rule here because x is in the base. So our rule says that the e comes down, and then we're going to subtract 1 from the power. So we get ex to the e minus 1, right? That one feels a little weird because it's an e, but that's what that first derivative is going to look like. And even weirder, when we do the second derivative, the e minus 1 comes down in front. And then we still have the e from before. And now we subtract another 1 from the power. So we get e minus 2. Okay. That one is a little, it feels weird because e is usually part of e to the x function, but here it's being used as a constant. So whenever you see an e or a pi, just think about how it's being used and where the variable is, and then use your rules to follow and just do whatever you're trying to find. Okay, so that one's a little weird. So if it felt weird or if you lost something, that's okay. That one's a little strange. For part C, we have f of x equals 6x to the 7th minus 20x to the 1/2. So I rewrote it as the 1/2 power. So my first derivative here, I'm going to start with my 6x to the 7th. So the 7 comes down, I get 42x. I subtract 1 from the power, so to the 6th. Minus, now my second term, the half comes down to multiply the 20, and I get 10x to the -1/2, because when you subtract 1 from the power, you get -1/2. Now, I can't remember if I said this before, but I'm going to say it again. If you are trying to get to a second derivative, you don't want to simplify the first derivative at all. You want to leave it as you find it, and then go ahead and do your second derivative. If you try to simplify the first derivative, then you're going to have to sort of unsimplify it to then take another derivative. So here we have 42x to the 6th, and we need to take the derivative. So the 6 comes down to multiply the 42. So that's going to be 252x to the 5th, right? If you need to do 6 times 42 on your calculator, that's totally fine. That's what I did, right? And then the second term, negative half comes down to multiply this minus 10. The negatives are going to cancel. Half times 10 is 5x. Now, negative 1/2 minus 1 is going to be negative 3/2. So my second derivative looks like that. So again, once I have my first derivative, I can apply the rules again to get information about the second derivative. Okay, so that's how the second derivative works. Let's see. We are going to skip ahead and then we'll come back because there's 2 examples I want to make sure you do before your mini quiz. So we're going to jump to example 8. Okay. And example 8 says, find the equation of the tangent line to the function x squared minus 4x plus 1 at x equals 3. So this is a common problem that we will ask you to do throughout all of chapter 3, and it will almost assuredly be on your mini quiz in some way, shape, or form. Not this particular problem, but find the equation of the tangent line. So I want to make sure that we do this type. Okay. So I want to remind you, the tangent line. How does the tangent line play into what we've been learning? Well, we know that the derivative is the slope of the tangent line at a point. Okay. So if the derivative is the slope of the tangent line, that's going to help us to get the equation of the tangent line. So the equation of the tangent line, because it's a line, is going to have the form y equals mx plus b. Okay. The derivative is the slope. So that means that by finding the derivative, that's going to help me find m. Okay. So what does that look like here? So the derivative of this function, again, I see it separated by subtraction and addition. So here, the derivative of x squared is 2x minus the derivative of 4x is 4. And the derivative of 1 is 0. Okay. So my generic derivative is 2x minus 4. But I am interested in the equation of the tangent line when x equals 3. So I need to plug a 3 into my derivative in order to get the slope. So I have 2 times 3 minus 4, right? So I get 6 minus 4, which is 2. So the slope of my line, my tangent line, is going to be 2. So we can start there. So we have y equals, we'll put this in red to show it's the derivative, 2x plus b. Okay, so again, the way we get the slope of our tangent line is to find the first derivative and plug in the x value that we're interested in. Okay, now we have the slope. The other piece that we're missing is our b. Okay, we need to figure out our b to have the final equation of our line. How do we get our b? Well, when x equals 3, if we are to plug this into the original function, right, we can get out the corresponding y value. So when we plug that in, let's see, we're going to get 9 minus 12, which is negative 3, plus 1 is going to give me negative 2. Now, why did I find that y value in the original function? I found that because that is the point where the tangent line touches, right? So we talked about how the tangent line touches the function at one particular point, right? Instead of 2 points. This is the point that it touches, right? Because at x equals 3. So why did I find that point? Because if the point where it touches is 3, negative 2, that point also has to be on this line, right? Because it's the 1 point shared by the function in the line. So now I can use this point to solve for b. So if I plug in -2 equals 2 times 3 plus b, and again, these came directly from my point here. I can solve for b, right? So this is 6. I subtract 6 over, and I get b equals -8. So now that I have my b, I get the equation of my tangent line, which is y equals 2x minus 8. Okay. So as I mentioned, this is a problem that we're going to do a lot of times in this class. What's going to change is the function that we're taking the derivative of and the point we're interested in. So a quick recap of the process of this particular problem. Find the equation of the tangent line. The answer will always be in y equals mx plus b form because it's a tangent line. To find the slope, we take the first derivative of our function and plug in the x value that we are interested in. That gives us a number, which represents the slope of the tangent line. In order to find our b, we plug the original value into the original function to get the corresponding y value. That is the point that is shared between the function and the tangent line. So I can then plug that into the tangent line, the y value for y, the x value for x, to get the b for that particular tangent line. Then I put it all together in y equals mx plus b form to get the equation of the tangent line. Okay, so those are the steps we're going to be taking whenever we're looking to find the equation of the tangent line. I am sure that this is on your homework, and there's a good chance that you will have one of this type on the mini quiz. So again, try the homework before you do the mini quiz. Okay. Let's look at derivatives of sine and cosine. If we have time, we'll go back to the earlier problems. If we do run out of time, they are in the videos that are asynchronous that are posted on Moodle, so you can look at them there. But we need to make sure we cover the things that you need to have for the mini quiz. So sine and cosine are sort of a weird add-on to this particular section. There's not a good place to add them on, so we add them on early. And it turns out that if you remember, sine and cosine are related because they're the same function shifted. They're also related in that if you were to take the derivative of sine, you end up getting cosine, right? That's weird. I mean, it's not that weird, but who would have thought? If you are to take the derivative of cosine, you get negative sine. Okay, so these are related, and what we need to remember is where the negative is, right? So sine, you take the derivative and you get cosine. Cosine, when you take the derivative, you get negative sine. Okay, so we add those onto our list of rules. So now we have that the derivative of a constant is 0. The derivative of a linear term is just the slope. We have our power rule. Power comes down, subtract 1 from the power. Derivative of sine is cosine. Derivative of cosine is negative sine. Okay, so let's do a practice problem that involves sine and cosine. Okay, actually, let's do 2 problems. We'll bunch them together here. Let's look at example 9 and 10. So for example 9, you want to compute the first and second derivatives. So the constant multiple rule and addition and subtraction, those are going to hold true for all functions we look at. So that means that that 6 in the first function is going to carry into the first and second derivative. For part B, we can see things separated by addition. So we can do them term by term. And same thing with part C, we can see it's separated by subtraction, so we can go term by term. So what I want you to do is find the first and second derivative for part A, B, and C. And then I also want you to take a stab at trying to find the equation of the tangent line of 3 cos x at x equals pi over 2 using that same process we used in the last problem. One quick caveat about the tangent line here. You need to make sure that your calculator is in radians if you're plugging pi over 2 into cosine. If it's in degrees, you will get the wrong value. Okay, so I'm going to give you about 3 minutes. Okay, try that out, see what you can come up with, and then we'll go through it together. All right, take about 30 more seconds. All right, so let's take a look at these and practice our sines and cosines. So starting up here, if we have 6 cosine x, we know that the 6 has to multiply the derivative of cosine. The derivative of cosine is negative sine, so we get negative 6 sine x. Typically, if we have 6 times negative sine, we're going to pull the negative to the front. It means the same thing. If we then want to find the second derivative, then we have negative 6 times the derivative of sine. The derivative of sine is cosine. So the second derivative here is negative 6 cosine x. So again, we're just really being careful with our negatives so we don't mess anything up along the way. Part B, we have sine x plus 1. The derivative of sine is cosine, and the derivative of 1 is 0 because it's a constant. So we just end up with cos x. The second derivative is the derivative of cosine, and we know that derivative of cosine is negative sine. And then for our third, we have this x cubed term that comes in. So when we take our first derivative, that becomes 3x squared minus, and then we have 2 sine x. So the 2 has to multiply the derivative of sine. So we end up with minus 2 cosine x. When we go to the second derivative, we take the derivative of the 3x squared. That gives us 6x. And then here we have minus 2 times the derivative of cosine. But the derivative of cosine is negative sine, and we had a negative 2. So those negatives are going to cancel, and we get plus 2 sine x. So our first and second derivatives look like that. Again, once you practice sine and cosine enough, you'll get more comfortable with those. Just be really careful with the negatives. Okay, so let's look at number 10. Find the equation of the tangent line to f of x equals 3 cosine x at x equals pi over 2. So we know that we need two things. We need the slope of the tangent line, and we need the point. In order to get the point, we're going to plug pi over 2 into 3 cosine x. Cosine of pi over 2 is 0. So 3 times 0 is 0, which means the point where the tangent line touches is pi over 2 comma 0. That's one piece we need. The second piece we need is the slope, right? So to find the slope, we need to find the first derivative. The derivative of 3 cosine x is going to be negative 3 sine x. Since the derivative of cosine is negative sine, we get this negative out front, and the 3 has to multiply from our constant multiple rule. And then here, in order to get the slope of our line, we need to plug in pi over 2. So again, if your calculator is not in radians, you are not going to get the right values. And so you definitely want to check your settings to make sure that you are sort of getting these correctly. So sine of pi over 2 is 1. This is 1, but then we still have this negative 3. So we multiply those together, we get a slope of negative 3. So now we have a point and we have a slope, so we need to put it all together. So y equals negative 3x plus b. We've added our slope. Now we want to plug in our point. So when x is pi over 2, y is 0. Okay. Now, whenever you have a pi or an e, you do not want to turn this into a decimal. Okay, you just want to leave it as pi. So we just need to add this term over to the left, and we get b equals 3 pi over 2. We're going to leave that in terms of pi for our answer here. So now putting this all together, I get y equals negative 3x plus 3 pi over 2. This is the equation of the tangent line for this particular problem, okay? So again, do not turn your pi's into decimals, leave them as pi's. All right, so I think we will stop here. Like I said, the 2 examples we skipped, 6 and 7 and 11 are in the asynchronous video, so you can go check them out, try out those problems at home, and then you can check out the answer there. Okay, have a great rest of your day, and I will see you guys on Thursday.